Hello, and welcome to Old School Coding. Now that I have the camera set up and the editor set up and the repository pushed to GitHub, we can start actually working on the code itself. I have a little bit of support code already going in the repository, which is very common for coding projects back when I was coding in the late 80s and early 90s. Not that I stopped coding, but this is the standard for then. The idea would be that you would pick up your build rules and your support code and your testing code, and you'd plop it down into a new place and start work. That's where we are. I briefly went over a few of the facilities that are available here, but that's not why we're here today. We're here today to start actually coding. I'm going to turn off the camera so we can see what's going on the screen. There we go. So, the fundamental design of this is a discrete event simulation, which means that at any given, our basic loop is to evaluate the state of the system at a specific time, and then move forward to a new specific time and evaluate any changes to the state of the system. And you repeat that loop over and over and over. Well, the system we want to simulate, and it should be in the thumbnail of the recording that we made for the first video in the series. I am aiming at simulating the Intel 8080 processor, and not at the instruction level. I want to go deeper. I want to be able to extract timing diagrams. Now, because I don't want to be basically writing Verilog from scratch and digging out the transistors of the 8080, this is going to be quantized. So our quantum is going to be one cycle of the primary oscillator of the system. And for 8080 systems of that time, a typical oscillator might be an 18 megahertz oscillator, such as was found in the MSI 8080. And that was used by a clock generator chip to drive a two-phase clock, which had a 500 nanosecond period. So there were specific clock edges coming out of that clock generator. So there's a rising phi 1 and a falling phi 1, and a rising phi 2 and a falling phi 2. And the actual 8080 chip has some strict requirements on the relative timing of those events, which we can, if we do this right, measure. So we can actually say in our simulation, are these signals changing within the timing constraints of the chip that we're simulating? So what I want to get out the other end is basically a timing diagram that looks like the timing diagrams in the manuals. But we're not going to be doing it with some sort of floating point time where I can say, well, we had a rising edge here, so 11.5 nanoseconds later we have a rising edge there. I'm going to discretize the time. So if we have a rising edge at time, say 1 microsecond into the simulation, everything that's triggered on that edge, we are going to simulate as if it happened at that exact time. So think of our time as representing not an instant of time, but a short period of time. And that period of time will be one time unit. For us, on the 8080, that one time unit is from one rising edge of the oscillator to the next rising edge of the oscillator. So for the system we're looking at, that is 55.555 nanoseconds. So yeah, one time unit is that long, and we will have to have a conversion to convert from that integer number of time units into some sort of measure of the floating point elapsed time. That will come later. But focus on what we've got going to begin with. We have a rising edge of a clock somewhere, which triggers some things to happen. A lot of circuitry that I built at the time, I actually wire wrapped and breadboarded my own personal computers at the time. Very tiny, very, very tiny, few chips. But everything was mostly edge driven. So you'd have a rising edge of something and things would happen, or a falling edge of something and things would happen. So focus on that. narrow it in. Things happen. A list of things happens. So we have a list. What is it a list of? It's a list of something that happens. So I'm going to call that a func. Our basic fundamental unit of operation in this simulation is a small function written in C, which is called, and it takes a parameter that is its context. So we have, say, a function that says the CPU has noticed a rise on phi 1, and it's going to take a context pointer so it knows what it's operating on, and it's going to do its job. So let us start out with defining func. Func.h. Okay, we're starting right off with what was a GCC extension at the time, pragma once. It says that if this file is included by more than one, it's included by a single source file via more than one path. So if I include 5 headers and they each include func.h, the compiler will only process it once. Sometimes you don't want that. For instance, if a header file does different things depending on how macros are set, you wouldn't do this. But for this, we do want it. So now I want to define what my function is. A func is going to be, actually, let's not call it a func. Let's call it a step. It's important to get the name right early because, remember, this is 1990. We're not dealing with high-end integrated development environments that allow us to refactor the name of a type across the entire project all at once. So basically, you settle on a name as you're building the thing, and you get the thing working, and you lock it all down, and you publish it, and the name of the thing is part of the API. And if you change the name, that's a breaking change. And in the modern notion of a semantic versioning, that would be a change from a 1.0 to a 2.0. That's a big thing because it breaks all the code that calls it. So once we settle on this name, we're done. So we have a step function. It's going to take a pointer and return void. Nice thing about C is I can cast a pointer to anything into a pointer to void. And I can cast any pointer to void into a pointer to anything pretty much without any problem. Up to me as an engineer to make sure that I don't take a pointer to one thing, cast it through a void star into a pointer to a completely different thing, because that would cause undefined behavior. But I don't like that void star there, so we're going to type def void star step argument pointer. So step AP is the pointer to the step function. And we don't really pass around functions in C. We pass around pointers to functions. So step FP is going to be a pointer to the step function. And I'm going to go over here, and periodically I will be running this build manually. We have a separate off the screen, I've got a script running that whenever it notices a change in the .c files, it will rebuild and rerun everything, and it turns out logs. And let me check and make absolutely sure that that's actually running. It wasn't. There we go. So if we make a change to a .c file or a .h file, then we will rerun the build, and it will generate log files that I can look at so that we have any errors in the build or compiler warnings, for example. You do a build, you get compiler warnings. Next time you build, it's not going to rebuild those source files. So you have to capture them when they happen. So we're doing that. Currently, the only log file I've got of any importance is runlivecoding.stderr, which has the standard error channel of the file. And all it's got is the benchmarking result for our real-time clock, which is a bit of support code. Performance is part of the requirements for many modules. So as part of our support code, we have enough support that we can test the performance of those modules. Anyway, so that gives us this for our definition of what a step is. So a step is a function taking a void star, taking a pointer to something that it understands, which returns nothing. So it's basically an operation on stuff. So now we need step.c. We need to implement something to do with step. So I included that, and that immediately triggered a build. And there were no errors or warnings or anything in that. So what do I want to do with this? Well, let's start off with testing this. I assert, as an engineer, that having one of these on hand and calling through it is really fast. So I'm going to write a function. I'm going to write a power on self-test function that verifies that it works, because I am that insane. Normally, one wouldn't do this for something this fundamental. So extern void step post. So we're going to have a power on self-test function like that. And as part of this, I want to be calling the power on self-test function. And here we have something called main.c. Currently, main is really very simple. It runs all the post stuff, it runs all the built-in self-test, it runs all the benchmarks. Later on, we will use command line parameters to limit what we do. That will happen once we get main as it stands taking too long for our build edit cycle. But for now, we're just going to add step post to our main. And if I save that, I'm going to get an error that step post isn't defined. And I am using a very modern compiler, which actually gives me a useful function rather than just a linker error of some sort. So we go down here, and I'm going to include step.h in main and recompile, and I look here and it's all fixed. So step post. Inside support.h, we have some support functions that I'm going to make use of. Print top and print end. These will not stay in post. Eventually, our post will be silent unless it fails, but for right now, I want to know that it's running. And indeed, if I don't #include support.h in this source file, it will have an error. So for now, we now have a build error that says our output from the program does not match the expected value. And the difference is that I am printing these two values. That's good. I want to have that continue to show up in the log so I can monitor here in this window any changes that I make here. Once we've got post locked down and we know what we're doing, we're good. So what do I want to do? Step.h. What is the power on self-test for this guy? Well, I want to verify that if I have a step function and a step AP somewhere, and I make that call, that step function gets called with that step AP. So let's define something here. Void, that's the static void, because if you don't mark it static, it becomes part of your global address space. I'm going to call this step post fn, and it's going to take I'm going to pass it a int star there. And what step post function does is it says plus plus star there. So all this does is it's going to increment what it has. And I saved it, so let's take a look at the logs. Boom. Step post function defined but not used. Now, there's another thing I want to do. My habit back then, which I still mostly follow, but back then I was strict about it, was high-level functions first, then low-level, which means you have to have forward declarations, or I had to have them, and there they are. Now, I think my logs Oh, this is done. This is running. Okay, that's good. So now what I want to do is step post caller of step post function and step post arg. And step post arg is going to be int. Little trick here, if I declare something to be an array of 1, its name becomes a pointer, but it does allocate the space, and I can initialize it to 1337. And of course, step post caller does not exist. And this is going to take a step function pointer and a step argument pointer. In fact, this is not just step post caller. This is going to be step run. So this is the first of my public APIs related to step. Usually we won't be calling through here. But for now, because this is the only function we have, this is the only module we have, I'm going to demonstrate setting up a new external thing. So step run is actually more important. This is all post-related stuff. In fact, what I can do is I'm going to take one of these big block comments, I'm going to put it here, and I'm going to say power on self-test stuff. Oh, come on. Did I do that right? There. So step run, declared externally here. I am going to define it here. What this is going to do is just FP of AP. This is mainly just to assure that I can pass these pointers, no matter what I've got here. I want to make sure that I can call a function that takes the parameters of that type and does something with it that's reasonable. So you notice that our external API, during the early phase of implementation, the details of the external API are strictly driven by our needs as we build the module and as we anticipate how we're going to use it. And that anticipation is done by looking at how we use it during the test. So during the test, we're going to say step run of something should do this. Now what we get is passing argument 1 of step run from incompatible pointer types. So we have to have a cast. So I'm going to make a macro that does the appropriate casting so we can call step run, well, sort of, found define step run of FP and AP is going to be step run of step FP cast of FP and step AP cast of AP. So you can do the cast, but you have to do it explicitly or modern compilers are going to warn you. Okay? This was perfectly legal, quote unquote, but it's also recognized as bad practice. And it took a lot of years for people to recognize that, passing a random typed pointer into a void star might be a sign of something bad. So we do an explicit cast to get that. So what have we got? Passing argument 1 of step run from incompatible pointer type. Still, because I didn't use the macro. I use the macro and the warning goes away. So the way we would run a step if we had those variables and we wanted to call a function to do it would be like that. But that does mean that we can use macros to cast the parameters through here and pass them into a function that takes them. Step run may go away from our external list. So there's our step post function is going to do that. We've run it, and I want to assert step post arg equals 1338. And it's the expression. So the assert macro I've got requires more than just the thing. Normal stock C assert, that would work. And if it failed, it would give you a line number and would point you at that. It would say nothing else. But we can do uppercase assert, and I can put a message here. And the message for us would be step post fail. Step post did not increment the counter. And I'm going to put a lot more information in here. Expected. And observed. And then we're going to say expected was 1338 and the observed was there. Now the reason why I'm doing this so verbosely is that at some point we will probably want to wrap up our comparison as an assert EQ or something. But let's get it working and let's use the same, use the same sequence, use the same bit of code in a couple of places before we turn it into its own function or its own macro. Okay, that cleaned us up. So what if I make this a failure? What if I expect a different value? What if I change this to be, let's try this 1335. Then that does indeed give us this failure over here. And if I hit next error on Emacs, it puts me right there. This assertion says this failed. Put it back to working again. What if the function itself is broken? What if I decrement it instead? Then it would, again, give us the failure. And we would see over here, expected 1338, observed 1336. I could look at that and say, oh, I know where that is. Okay. And apparently in my indent profile, I say that the pre-decrement operator must have no blanks before its parameter. So that's what it looks like. My style has evolved slightly since then. I actually went back to a really old version of the Indent Pro for this. So there's our power on self-test that verifies that we can call a function once with one value and that it works. So next step is I want to do a built-in self-test. Now, this is going to do more things. I'm going to have more than one function available. Well, actually, yeah, more than one function available and more than one argument available so that we can make sure that we're actually calling the right function with the right argument rather than maybe somebody is doing some jiggery-pokery in the middle there. This will become more important when we have something stateful. For now, this is just synthetic. We need the functions to do something slightly different. Let's say increment by 10. And increment by 100. Again, we're still working on trivial stuff here. Kind of trying to basically ring the changes through on how we're going to be doing testing while we have something really, really trivial to test. And 1, 2, 3, this is going to be plus equals. one. What's really funny is I often get down on the test-driven development people for writing absolutely trivial tests that have no meaning. And here I'm doing the same thing, but that's because what I'm doing is I'm developing the actual test mechanism while I'm doing it. So that works. Again, evolution of your tools is part of your development process in this particular historical narrative. So where did I define assert? There it is. So I want to define assert equals and actually I need to break this up a little bit so that I can write something a little bigger. It needs to be a macro. Okay. Currently we won't build because I need some backslashes in there. But what we want to do is the equivalent is not a condition. It is a expected and observed. And what we say here is if expected is not equal to observed, actually if it's equal to, I'm going to keep this layout so that we can take out the do while. So one way of doing this, if you've got a lot of complicated things in the macro you want to expand, is do a do while with no ending semicolon. So literally the next thing on the program pretty much needs to be a semicolon there. But something like this where we're checking the condition, that's fine. Expected, observed. What I'm going to do is I am going to write my own message. So assert EQ is going to handle providing the message. So what we have is it's going to say the file name, the line number, and the function just like it did before. And then what we're going to say is condition failed, or comparison, equality, comparison failed, expected, value. Again, so because we're doing a printf of the expected and observed values, this is going to be different depending on the type. So I need to put the type in here because this is not C++. We don't have nice macros. So I'm going to do an integer. So I'm going to expect these to have integer values of some sort. But I don't know what they are. So I am going to cast them to long longs, which is the longest integer type natively supported by the platform. Often this is two longs. So for instance, classically a long might have been 32 bits, and a long would have been the huge 64-bit value. Modern CPUs, often long is going to be 64 bits, unless you're on Windows, where long is still 32 bits. God knows why. I much prefer to have the size of long be the same size as void star. So I am a what's called an I am called an LP type is my preference. So you've got ILP 32 is integers, longs, and pointers are all 32 bits. And you've got ILP 64 where its longs and pointers are all 64. Then you've got LP 64 where int is smaller but longs and pointers are 64. Anyway, there was all sorts of conventions for expressing that, and nowadays you just use ctype.h and grab the right thing. But we're going to do long u, and I'm going to, in parentheses, put the expansion of that. See, I can use a string eyes operation to put the value there. So we're going to say expected value is long expected, like that, and observed. And now we can take away all of this guff. I'm going to reduce the length of these names so that my macro has well, I could reduce the length of the name so the macro has a chance to fit on one line. Or I can accept that it doesn't, and I'm going to do that latter. So, start a keyboard macro, end of line, out there to some column. So this is what the macro would expand to, and now I can say assert EQ integer of expected is 1338, step bist arg1. Oops. 338, 1347, and 1447. 1, 2, 3. That replaces all of those. And for some reason, implicit declaration of assert EQ integer. I used EQU here and I used EQ over there. Called object is not a function or a function pointer. So it's saying that on this line of this macro, because silly me forgot a comma. Well, one of my habits back in the day was after my format string, I would put commas on the leading part of this. That gave me a couple things. First of all, it meant that I could add more parameters in the middle, and only really the last one knew that it was last. And if you did that, you could even add more at the end by putting the closed paren on its own line. So each line was comma this, comma that, comma the other. Your formatting string was different in that it didn't have any commas in it. It didn't end with a comma. You could add more stuff onto the end. A lot of my printf lines would tend to grow. And I just realized that if anybody is tuning into this, I am not actually monitoring YouTube at all right now. So I'm going to take a moment to bring up my channel and see what is going on. Make sure that if somebody actually does come in, I will notice. There we go. So yeah, I will have to glance over to the right from time to time because I don't think anybody is going to be watching this live yet. I don't normally stream. So if somebody does tune in, I want to notice. Maybe someday later on, after I've got a few of these under my belt, I will start getting people tuning in. And at that point, we will have a community, maybe, maybe not. So what have we got here? This says, passing argument 5 of underscore fail makes pointer from integer without a cast. One, two, three, four, 5. And macro expansion of there in step. I am not sure what it's complaining about there. Oh, right. this line is much more indicative. I am calling fail file line function format data. File line function cond format data. If I do that, that breaks all of my assert calls. Let's take a look at the actual fail function, see how I can make this come together properly. That is, I suppose, in support.h, it's called _fail. And what it prints is file line in function test condition failed, and then something in parentheses. So let's keep cond here. And I am going to write in here found observed expect it like that. Okay, that was not good because a pound sign as the first non-blank is going to be ugly. Now, back in the day, I actually had to put a special operator in here to paste them together. Modern C compilers, I believe this might have been standardized in C99, but I would have to go back to check whether it was standard or an extension. String literals, one right after the other, did get concatenated. So this looks like it works. It does indeed. So let's break it. So I can break this by either changing the initial condition up here or changing that. So what I'm going to do is going to say int const int val equals 1337. I'll actually call this start val. Oops. And this is start val plus 1. So in the general case, whatever value I hit here for start val, it will verify, and it should come up with a pass. So the way I break this is by going in here and saying start val. Let's modify it. And what we see is that my modification is not causing it to fail. So this says if expected is equal to observed, nothing else fail. See, this is why you run tests, because, like I said, something I've done here is not as I expected it. So I'm going to toss in a quick abort here. Ah, there we go. This else does not guard. Well, that's because the abort is inside the else and the fail is not. There. That gets us back to a running system, and it is not hitting that abort. Which means this is not doing what I expected it to do at all. So what I'm going to do is I'm going to put something in here to print as well. Test passed. And we're going to do the same thing here. Expected, observed. Else. And we'll go back to this. So I should always see one of these two. So we are getting to the top of the step post, and we're getting to the end, and we're passing through this code, and yet neither one of these is being printed. Which is very troubling to me. So we go further. Just comment this stuff out for now. So I am really scratching my head here. Okay, I have been doing this in step BIST, which is not yet being called. Oh, Craig. So I violated a rule. when I constructed step bist, the first thing I should have done was to verify that step bist was being called, and I did not do that. We're done with step post. We can get rid of those. We now have step bist, which should print, do this, and do that. We have main bist calling step bist. And we are indeed getting this aborted, which means I am getting here, and now I can start undoing all the debugging I was doing. Assert EQ integer, comparing those. That looks good. That's better, and now we cause the test to fail, and there it is. Okay, so this is typical of the debugging loops I was going through back in the late 80s and early 90s, is that as you work through these things, the problems that take you the longest to solve are the ones that had the stupidest causes. So, there you go. Oh, I see Rob has joined. Forgot to call the top level dist function. So there we go. Hi, Rob. So yeah, if you don't call the function, you can't get it to fail. Right. So you get rid of that. And now we're back to working. Again, trivial code. But what we did was we wrung out a couple of things. We got our change to our test macros that allowed us to do the equality comparison of integers. And we actually exercised our mechanism, our actual methodology, by failing to follow it. So I failed to make sure we were calling step bist before trying to debug what was going on inside it. So the next thing I'm worried about is benchmarking of it. And again, this is pretty darn trivial. So what we're going to do is we're going to extend this to be a benchmark. I really ought to bind center line to a key. I use it so rarely. Okay, so step bench. Now what we want to do is basically run one of these step runs over and over and over again. I'm going to do all three of them. So during the benchmarking, we don't actually do that. Oh, and now that we've got the BIST done, I can take out the macros, the print when we enter an end. So our BIST is going to be silent in this case. Because this is a quick one, we'll just be silent. If there's a failure, it'll say. So we do have a benchmark already set up in RTC. So there's some key logic over at RTC here, which basically increases the number of reps until we've gotten on long enough. Now, what I really want to do is take this entire framework and repeat it for something in here, but we're going to do that over and over again. So what I'm going to do, is I'm going to set up a bench that takes a step and runs the step over and over again. And we're going to use that later on so that future benchmarks can package up what they want to run within the benchmark as a step. So this will be an extension to RTC that uses step. And there's a question of where we should put that. So what I'm going to do is I'm going to say we now have a public API to step called void step time. In fact, I'm going to return double. I'm going to call this step time of FPAP. I don't want to call it step bench because step bench is the benchmark for step. This is a step timer. Call it step elapsed. And we're going to pick up the RTC benchmark from here. Whoops. There we go. Same logic, but inside here, instead of RTCNS, we're going to call FP of AP. Now, I could say step run of it, but we're not benchmarking step run with step elapsed. Okay? So, with that in place, we're going to use this in our benchmark. Now, in a moment, we can't do a power on self-test of step elapsed. Not unless we want to pass in what our target time is, and even then, it might end up driving our runtime longer than we want in a power and self-test or on a benchmark. But we're only going to be calling it from a benchmark. So I think we're good. So what I want to do here is, this is actually called step bench all. It's going to ignore its parameter, and it's going to do step run of all those guys. So now we get down here, we say step elapsed. And what we're going to pass it is step bench all and a 0. Now, of course, incompatible pointer types, which means we have to do this. Actually, come and grab step run. Oh, we already did. Just like that. And now we have a step elapsed macro. Warning, unused variable. So I'm going to, okay. Standard error output is going to be displayed as part of the build and the build logs. Standard out is going to be compared with previous stuff. So if you send out just normal standard out, it has to be the same from run to run. This isn't going to be the same. So fprintf. Actually, let's use the step macro. .3f. dt is going to be, what is it here when we do this? So dt times 1.0 over max reps gives us nanoseconds per call. Well, that's what we're returning. Haha, I forgot to return it. There we go. So it's floating point nanoseconds per call. Okay, and this guy. Oh, these guys are here, but they're used down here in this guy. So How about we do this? We've got 3 counters. Got an array of 3 integers being passed in. That's better. And void star dummy, we don't have that anymore. Okay, so now we need to actually call step bench. So over in my build system, it is running for a very long time doing this, which means it is likely that I have a bug in this benchmark. Let's take a look at it. So T0 is RTCNS, T1 is RTCNS. If DT is greater than target nanoseconds, we break. Otherwise, we adjust max reps. I'm going to break. I interrupted my build scripts. Let's take a look at what we've got going on here. We've got nothing. So we now need to diagnose why this is taking forever. Well, because step elapsed, let's see. Step elapsed macro is calling the step elapsed function. So it appears we are getting to step.c. We're getting here once. Then in step bench. Okay, suddenly it's working. So I added the printf, and suddenly it's working. Unless I simply missed it earlier. So let's take out the printf. Okay, this is really rich because it's looping forever now. I put the printf in and it terminates. I take the printf out and it loops forever. Oh God. Hello. So, what is different about having stub here versus not having stub here? Let's take a look very carefully at the stub macro. What does it do? It does a function call, passing these parameters around, along into the function call through of our args macro. If I move it, it still works. If I change it to just print, it does nothing. Now it's looping forever inside live coding. Okay, so the question is, are we getting down there at all? Are we never returning from something? So let's start off by putting something in here. This should repeat the word hello over and over and over again, but it'll be part of, okay, that works. What that ends up doing is printing out all those hellos. It takes long enough that eventually we are done. Let's make it just one character. Okay. Actually, let's make it a dot. Okay. So if we print something from step bench all, it does do something. Let's move it down into the end of FN3. So that's not enough to fix us. Okay, so it's at this point in the evolution of a program in 1990 that you finally decide to give up and run the debugger. So I'm going to put this in the state where it's running forever. There we go, and we're going to go GDB. And what we're going to run is bin/live-coding. And we see the output over here. Oh, let me stop that version of it. So we did reach there. Now I'm going to interrupt it over here. And we are in clock get time, which makes sense. That's where we're spending most of our time. Okay. So here we are in step elapsed, so we are reaching that point in elapsed, so we're not looping forever. I wonder if it's just so bad. Ah, there we are. Yep. Okay, so back in the day, I never would have seen this, but these days, our CPUs are so frippin' fast that max reps gets too big, which means that step elapsed needs to be ready for max reps to overflow in any of these calculations. So one thing I'm going to do two things. First of all, I'm going to make max reps a 64-bit integer. But before I do that, I'm going to whine if max reps is less than or equal to 0. Okay. Turn on the build again. Terminate GCC. And this is saying argument type 1 of 3. Yeah, okay. So I said arg sub 3, and GCC was telling me, oh, yeah, you've got mismatched bounds. There we go. So if we use int for max reps, we do violate this because we will be increasing it and overflowing it. So I want to make max reps type tau. This is only going to happen if it takes more than 2 to the 31st, more than about 2 billion iterations for our benchmarks. And this is still triggering. How about that? How about I write this correctly? So I don't know if that actually was failing or not. But my hypothesis is that we had an overflow. And with that change in place, it still loops forever. How about I assert that it's greater than 0? If max reps becomes 0, we're in trouble. Well, there's part of it. I got a G inserted in a piece of source code. So we are still looping forever in this function. So there's our output. Here's what's happening. dt is stubbornly staying low. So what's happened is that for some reason we are not looping here. Okay? Somebody has optimized it out on us. So we see on the left, max reps 1,000, 0.04 microseconds, 10,000, 0.02 microseconds, and so on. So this is literally doing nothing. So we're going to start here, actually. Step elapsed. FP is equal to %P, AP equals %P. I'm beginning to think that what's happening is that the optimizer is inlining step elapsed, and all of the functions are getting collapsed out, and it's saying, oh, we don't need to actually do that. And that's bad because the function I'm calling actually does work. It actually does something. It increments. So I am calling it with step bench all. Step bench all is a real function that takes a parameter and does real things on them. Oh, and this buffer has now gotten long enough that it's giving Emacs a bit of a headache. There we go. So the act of printing out this function has caused my benchmark to run rather than not run. And I think that's because step bench is getting it inlined. So what I'm going to do is I'm going to take this and I'm going to put it in a separate file. Okay. Now we're going to go back to step, and I'm going to take the printfs out, just that one, which is the one that made the difference. And what we see now is that we have build errors. So it's very important that step elapsed itself does not have the function inlined when it's benchmarking the function. Now, only step would have this issue. But I think better than putting step bench out separately would be to take step itself, and I'm going to take step elapsed out into a separate file. Like that. Do a make clean. Make sure that my build loop is running, because I had to terminate that a few times. And now we get to clean up the errors here because I took step elapsed out. There we go. So that's working. And what we're seeing is this is taking 14.952 nanoseconds to call that function, which made 3 calls. That's fairly fast. I've seen faster. And that time will vary from run to run just slightly. So there's step.h and step.c, step bench. So now we have the facility that allows us to call a step function. The next few things we want to build. Each signal has a number of people that subscribe to it that are going to want to receive notification that the signal has changed. So what we want is not just run this function, step run of this, we want to run a bunch of them. And the next thing we think about is, I'm all the time passing out FP and AP. Let's step back and do a little bit of refactoring. I'm going to define a structure which is called a step. And I'm going to use a funky little trick here. In some places, I'm going to be passing around a pointer to a step. In other places, I'm going to declare storage for a step. I want to be able to use a variable the same way, whether it's a pointer to one or an instance of one. So I'm going to declare the type as an array of 1. And this is going to contain a step FP called with FP and a step FN, FN, like that. Now at this point, all these functions that are taking FP and AP are now going to take a step. We no longer have the macro because we're not going to, it'll be, people will have to construct one of these structures now. Step S. So this is a breaking change to the API, and it's not building. Of course it's not building. And what do we need to do to get it all working again? Well, step run now takes step S, and this is S arrow A. And notice I can declare my parameter be of type step, which is an array of 1. Okay, step post. Now I need to actually create a step. I keep getting caps lock on. Now I'm going to actually have to go through and fix all the syntax on this entire thing. Comment change. Never want to inline into the function that is measuring elapsed time. So what I'm suspecting is that GCC inlined. Let's go over this in detail since this is a really interesting case. So we had a loop that ran this function a bunch of times, a known number of times. So GCC inline step bench all into that function. And then it said, well, we're running this function and this function and this function a known number of times. So it's going to inline all three of those functions because it sees what it's doing. I mean, it's inlining step run. It strips away the cast, inlines all the rest of this stuff. So it has a loop. The increment's there by 1 or 10 or 100. And it scratches its head and says, well, if I loop 1,000 times increment by 1, I can replace that with increment by 1,000 because nobody said it was volatile. So the benchmark loop resulted in GCC emitting increment step bench arg sub 1 by the appropriate number and 2 by a different appropriate number. So literally it didn't loop anymore. So you cannot allow the compiler to inline anything into your loop that repeatedly runs something. This has to be sacrosanct. I am willing to say, yes, GCC can unroll this, but it has to make the right number of calls to that function. It cannot inline it and strip out stuff that's not needed. So unless there was a GCC pragma that said, never inline this call, we have to do it by having step elapsed out here on its own. So when it's compiled, it doesn't inline it. And when anybody else calls it, they have to use this version that was compiled. It's a trick from benchmarking that has just been a pain in the butt. And Rob, attribute no inline, yes, I could use that. But I'm trying still to stay in the 1990 time frame where we didn't have attribute. And yes, that's how it is solved. That's recent enough I didn't even know about it. So yeah, attribute no inline would do it. Now, is that an attribute I can put on the call? Could I put it here? Can I mark this as never inline? If so, If so, I could do that. If not, I could do a step elapsed helper where we'd call the step elapsed helper with this, and it would make the call. We couldn't inline the helper. I'm thinking defeating the inliner. It's on the function definition. Okay, that's what I thought. So if at all possible in the actual simulation, I want it to be able to inline step functions. But for the benchmarking, I don't want to inline the benchmarked function. So I wouldn't want to mark that. I would have to mark step bench all as not being inlined. I wonder when that was invented. I might be able to get away with using attribute no inline. Tell you what, if that was available before 2000, I'll use it. Okay? Let me do a quick Google. So, hello, Mr. Google God, Mr. Font of all knowledge, true and false. When was attribute under attribute no inline in start available? Okay, so Stack Overflow has a question about it in 2009, so it might be old enough. GCC 413. I recall using GCC 4 way back when. We are doing this. Okay, so step elapsed. Goes back into step.c. Boom, boom, boom. So I still need to fix the call. So this is still a step S. And this is still S arrow FP calls S arrow AP. Now what we're going to try to do is get this to fail again in the same way before I mark this as no inline. We'll mark this as never inline. So step S, where else do we have raw function? Well, obviously in all of these places. Step S1 equal to step bist fn1 and I am betting that these step initializers are going to be a macro because they're probably going to need a cast. So now we say step run boom. Okay, this is step FP. Okay, so haha. Okay. Fix the name. Okay, so these initialization from incompatible type. So what I want to do is pound define step init of FP, AP as brace. Pren step FP like that. Okay, implicit declaration of step init because I didn't save steps fast enough. Missing braces around initializer. Okay, the other trick is that step declares S to be an array of 1, so we need double braces. There's another reason for putting it inside a macro. So now I'm going to fix these up by doing a keyboard macro that says, go to beginning of line, select equal brace. This becomes step init left paren. got multiple error warning, multiple warnings on all of these. So let's just do this. Step bench. Now these guys, step bench all, it's going to require 3 steps. This is leading towards us carrying around a lot of lists of steps. But for now, while we're doing this, there we go. Now step bench arg is actually going to be these 3 steps. Just like that. And that's actually legal. So we have an array of 3 things, each one of which is an array of 1 thing, which is initialized like that. So now inside here, what we're going to get is a step arg sub 3, and we're going to say step run of args sub 0, 1, 2. We're actually shaping up to the first, to the next data structure we're going to be doing, which is a list of steps to run. Okay, so initialization of void star from an incompatible pointer type. This is a what? Wait a minute. This is the way I want the declaration to look for an array of steps. Near initialization for step bench arg00 fp. Unused variables, yeah. So it's not complaining about these initializers, it's saying that they are unused variables. That's fine. An unmatched bound, fine. Conflicting types for step bench all. Where? What? Unused, unused, unused. Oh, right. Want this to be a pointer to a step, where a step is an array. So this should be correct. I believe, yeah, I forgot to put in a definition here. I inherited this from a earlier version of the code that is actually much more advanced at this point. So we are going to put in step up here with tau, and the rest of this is going to go away since we don't really have it yet. Rob, I see your comment. It's a function of yeah, that would be an alternative. What I want to do is I want to have the compiler have free reign to make things fast. So if this is the only place where I need to worry about the inlining thing, then I will just put the declaration on it and we'll be done. But for now, I have this problem. Oh, I know what the conflicting type is. I am such a Goomba. Remember what I said earlier about the stupid problems being the ones that are hardest to catch? I forgot to change the forward declaration. Okay. So now these functions are defined but never used because I never called through here. So we're going to pop that out and reinstate this and see what happens. So initialization of pointer to function from incompatible type. So this is still doing the wrong thing with step. It's almost like it's unwrapping. Yeah, it thinks that I should have extra braces there when I shouldn't. Oh, right. I don't have an array of 3 steps. I have an array of 3 pointers to steps. There we go. That works. So if I wanted to have an array of 3 steps, which would actually be a different thing, I would do this. But inside here, I would need these guys, which actually is not a bad thing. I don't think I would normally do this. The step list that I'm going to be using in the simulation can be dynamically generated at runtime by initializers. So S1, S2, and S3 now go away. And I'm calling step bist instead of step bench. So bist becomes bench. There we go. Huzzah! And you know what? I think the inlining might have been exacerbated by the fact that I was using step bist, which is a much smaller function. No, step bist, the same thing. Okay. So at this point, we should be seeing the same problem. And what I want to do here, how about I get rid of these arrays because it's a test. Int step bench arg sub 3 equals. How does that look? That looks better. So as a result of doing all of this, we now get a nice honest 3.28 nanoseconds per step bench all call. That is faster than we had before, significantly faster. My experience is that if you are setting up a lot of arguments on the call stack, at least on x86, it does slow it down a bit. So the other thing I want to do is mirror this back up to bist. I'm going to replace bist with the current bench and just add in these asserts. Not power on self-test. Oh, I forgot to change the comment. So I want to use the same logic here that I used in the benchmark and add in the asserts. You know, I could unify all of my little step functions. I don't need step bist function and step bench function. It's all the same thing. And down here we're going to say functions picked up for testing and like that. So now I've got multiple definitions that are identical. So post is just going to step run one step and verify it did something. Bist will pick up this logic. But instead of running step elapsed, I will run step run, a step bench, and we're going to assert things. These are common to benchmark and testing. So built-in self-test and benchmark are very similar. The difference is whether I take the elapsed time. Okay, difference here now is, well, obviously, step bist arg1 is now step bist step args sub 0, and so on. So now you notice we have printouts that we entered and exited the bist and the step bench. I can eliminate those now because I know we're actually getting there. Step bench is sending its output to the error log properly. And there we go. So step fn all, this means we're doing indirect call to a function, which is doing indirect calls to 3 different functions. And those indirect calls involve fetching the function pointer and the parameter pointer from this step thing. So I think at this point I'm going to take a break and have some dinner, and I'm going to come back and I'm going to start up another live stream where we're going to start doing something more with step. I'm going to start building up the step list, which will be the root of when a rising or falling edge happens, we run a bunch of things. So we're going to step up list, which is going to be expandable list of sequential steps to run. And it's going to be based on this step fn all, although it's going to be a loop. It's going to have some storage. It's going to iterate through. It's going to be able to expand the storage. So I will be back for that after I have some dinner. And I will see you then.